Okay, hello. This is Shubhang. It's 17th of July 2024. Welcome to the first Thesis Byte. Um, Thesis Bytes is a routine that I want to introduce for myself, where I talk about small progresses that I make in the thesis that might seem very small compared to the goal that I'm aiming at globally, but but the the small progresses, although they give little joy whenever you try to solve them, calculate them, but sometimes it's nice to have a reward sort of thing for those small progresses. Um, progress, small progress. So this Thesis Bytes is a initiative for me and myself where a byte, a recording of a byte is a reward for me, sort of reward for me. It'd be it'd be nice to keep track of these things. I'm not sure if I'd be able to do all the things, but at least some of the bytes I could discuss, right? And one more thing, yeah, and this could also act like my thesis blog sort of thing, blog sort of thing. So there's that. And yeah, and regarding the management of the thesis work, I realized that there are a lot of chains of thoughts that you need to go into, the web of thoughts, the web of directions that you have to keep track of, and you may not always be able to go to the end of every chain of thought and chain of desire to solve things, understand things. So you have to keep in mind where you want to go and where you're able to go and where you need to take a pause, where you need to stop, where you need to move ahead. So these are sort of things that it gets difficult to keep in track in your mind. And of course, the first thing that you could do is maintain a thesis journal and write in that, which I am doing. But um, this is 21st century, and there is this thing called Obsidian, which makes things easy for you, which which gives you a canvas where you can add cards with necessary to-do lists or titles and markdown. Basically, it accepts markdown in these cards, and also you can add notes on the canvas. You can link them, you can backlink them, you can add photos, you could add web pages, you could add videos and everything. So that's what I'm going to do. I'm going to build my canvas, and I already started doing that around since almost a 6 days, maybe around 6 days ago. I started doing this. It's a nice process. I'll show you how it looks like, and yeah, and it's very clear for me to decide on the bytes that I want to discuss. Right? It's in this canvas. Okay, when you make a canvas, it's clear for you where you're heading at, where you are heading to, and where are you stuck at, and why are you stuck at. These things are become apparent in this canvas. So let me show you my canvas. So the at the center you see yeah, you see the thesis, the main thesis title. I'm working on ADS safety correspondence. um, So, area safety correspondence is about the correspondence between a theory of gravity on ADS space-time, anti-de Sitter space-time, whose boundary, when you look at the isometries of the ADS space-time, and when you look at those same isometry on the boundary, it acts like a conformal group. So there is this conjecture of correspondence between the theory of gravity in the ADS space-time and a field theory whose symmetries are given by conformal invariants, conformal transformations. So a conformal field theory on the boundary of ADS, right? This is the correspondence. Uh, there are many elements that come into this, which I'm not yet uh, aware of course. There is no field theory that I'm doing right now. I'm just trying to, the first thing that I'm trying to understand is the geometry of 8 space-time. I'm working with Dr. Yogesh Srivastav here at NICER, and yeah, uh, he assigned me the first topic of geometry of 8 space-time. I could start reading on that. So 8 space-time is anti-de Sitter space-time is a solution to Einstein's field equations when you have a cosmological constant, and anti-de Sitter space is with a negative constant negative curvature surface. This is a constant negative curvature surface, and yeah, depending upon your sign convention, this either means your cosmological constant is greater than 0 or less than 0, right? That depends on your convention, but curvature thing remains. This is that the negative curvature, constant curvature, gives you the anti-de Sitter space-time. Okay, so, and then geometry of 8 space-time, there are many elements in that. If you first talk about 8 as a solution to Einstein equations, then you go into how do you describe the solution now, right? How do you will solve the field equations, and you will the first proposition is that you consider 8 space-time as an embedding in a higher dimensional space-time. For example, if you're considering an 8 n plus 1 dimension 8 space-time, you will have embedding space as an n plus 2 pseudo-Euclidean space, and pseudo-Euclidean space, and then the boundary of 8 turns out to be an n-dimensional thing on which your conformal field theory will be discussed, I suppose. And then you can give many coordinates on 8 space-time, different metrics. You can see the various forms of metrics on the 8 space-time, and we'll discuss useful coordinates on that, probably in some bytes, but yeah. And then you have the boundary of areas discussion, which is important gateway to the next steps, which is related to the conformal algebras, and how do you discuss the boundary of an 8 space-time and all that. So the cyan colored ones are the 4 channels to which the geometry of 8 space-time led me to. These are majorly the four parts of this main resource that has been given. This is the Introduction to Malus-Dennett Conjecture on 8 CFT by Peterson, J.L. Peterson. It's a good read. It's just few sections. It's the second chapter and few sections on the geometry of 8 space-time, the basic elements of this. And let me just give you a bird eye view of how the canvas looks like at present. This is how the canvas looks like. You could see the main thesis channels from here. You have some to-do lists. I made a to-do list, and then you have a shiny object syndrome wala thing, where you get attracted to various things and you want to read them. Sometimes that is necessary and sometimes that is interesting. And the main channel, geometry of area space-time, and divided into 4 channels. And the first I'm still in the first thing, I suppose. No. So for the last 3 to 4 days I've been working on the first channel of geometry of area space-time, which is IDS as a solution to Einstein equations, where I had doubts. Actually, I did read all these 4 channels before, and to that paper by Peterson, a review article by Peterson, where these sections were discussed, and I had questions, and I had to look into the details of all those things. So ADS as a solution to Einstein equation has a lot of channeling here, as you can see. So maximally symmetric spaces are what I've been working on in the last 3 days. Okay? Interesting stuff. Lots of doubts too. Okay, I'll be discussing some aspects of this. Okay, so that is how it looks like. So that's how channel looks like. Channeling and thoughts and web. It's clear for me to see where I'm stuck with those red marks, which things have almost been solved, and The purple indicates some reading to do, naughty reading maybe, and yellow is some juicy work to calculate my own thoughts out, and red are obviously the doubts, and yeah, that's how it is. And now I paused this maximal symmetric spaces with the part 3. I thought it's a good time to pause this and move ahead to ADS to learn more about the very ADS spacetime and de Sitter spacetime and all that. But before that, I actually went to the conformal algebras, because it's just a chapter behind those things. So I started with conformal algebras. That will be a next byte. Okay, so okay, that is fine. Okay, so I'll discuss about maximal symmetric spaces for a few minutes now in this first byte. Yeah, and that's how the whole canvas looks like now, as of now. Interesting. So let's move on to the discussion. Okay. It will be mostly a summary of things, nothing else. I won't be explaining a lot of stuff. I'm just giving a summary of things. So the main motivation of why I'm studying, how I got into, not motivation, but the reason why how I got into this study of maximal symmetric spaces is because the Peterson's review thing. It was written that the ADS spacetime will also looking for a maximally symmetric ADS spacetime. So maximal symmetry, as we'll see, it makes sense to ask that condition, demanded condition, and that's how I got into it. We are looking for maximally symmetric solutions to Einstein's field equations, and I'll discuss what maximal symmetry means. Okay. Okay. So the story starts with killing vector fields. Okay. So story starts with killing vector fields. Actually, what are killing vector fields? So before that, we look for something called isometries, right? Isometries are the coordinate transformations, which preserve your form of the metric. To write it explicitly, if your transformation is from x mu to x prime mu, which is equals to x mu plus epsilon xi mu, let's say this is an infinitesimal parameter, and this is your transformation, right? This is a x dependent quantity, and now by isometry we mean if this transformation preserves the form of metric. And how are we doing that? Is by just a second. Yep. Just by demanding this equals to sigma of x, which is equals to, as we know by the tensor transformation of metric tensor, is just this. Okay, this is the isometry condition. This is the isometry condition, and we demand this. Now, okay, wait, this is this, yeah. And now you could substitute this transformation here, and an interesting thing that I got to know yesterday was, if this is your transformation, then this implies, interestingly, x mu by del x prime rho is nothing but del mu rho minus epsilon del rho xi mu of x. It's interesting. Okay. I mean, you could solve it to first order in epsilon, you get this simple thing. So you substitute this here and all that, then you get an equation which we call the killing vector field killing equation. I guess killing equation, that's what we call it. It has two forms. First form could be written simply as this. Again, remember, isometries are something that preserve the form of the metric. Just the form of the metric. What do I mean form of the metric is this. And this could also be written in terms of covariant derivative as I don't know, yeah, this looks fine. Yeah, this is first form, this is the second form, if you will. So, and these psi's are called killing vector fields. And this is the killing condition or killing equation, whatever. Killing vector fields. So basically, killing vector fields are nothing but those vector fields which, when you follow the transformation in those directions, you get an isometry. Yeah, and isometries are good because they preserve your metric. You go to a familiar place. Familiar, what the hell? No, sorry. Familiar place, just a, yeah, you change coordinates, your whole metric changes into something more simpler or complicated, but again, it's just same thing. I mean, it's the form is still invariant, and yeah. Isometries are important because they also give you conservation laws, which I'll probably deal sometime later, which you can see. It's part 3 of this. Okay, yeah, it's part 3 of Maximal symmetric endeavors, which I will get into sometime later. For now, it is paused, but I'll understand this symmetries better. So yeah, so then we looked at how Euclidean space what isometries you get. It turns out Euclidean space is a very simple case to solve these things because you know your metric, right? You know your metric, diagonal 1 1 1. That's it. And to solve these equations, you get your killing vector fields, and which are simply the generators of rotations and translations. You get 6 in Euclidean space, and then you could take S2, where you do get some non-trivial vector fields, but as you know, it's still, again, that is also maximally symmetric in some sense, and you get all the translation and rotation killing vector fields. The same thing, you use the g theta equals to 1 and g phi is sine square theta. You get the whole killing vector field conditions, and you solve them, you get a rotation around psi phi, and you get two translations sort of in two directions, which are some non-trivial combination of thetas and phis, cos thetas and phis, which I will not write here, but yeah, you do get two directions here, and that's good. That's the first part. Now if you look at the second part, where you can you question the maximal symmetry, right? How what do you mean by maximally symmetric space? So for that, you define first the notion of homogeneity and isotropy. Homogeneity is if spaces are homogeneous, if at any point you have a transformation that takes you another point, if at any point there exists a kv of xi, which killing vector field, which takes it to some other point, a translation kvf perhaps, which takes you Yeah, the very fact that there exists a killing vector field that translates this point to some other point means that this transformation is an isometry, because you're saying there is a KVF, killing vector field. There's that translation at every point. This is homogeneity and isotropy, which was kind of tricky for me to understand, is the existence of rotational KVFs around each point. I mean, it fixes this point, of course, but rotates the surrounding points. Um, but yeah, z of x is 0 because this point is fixed. And there is a non-trivial definition of isotropy where you define it to be the existence of the rotational KVFs around a point, fixing that point, and whose derivatives span the and whose derivatives actually span the antisymmetric d by d antisymmetric matrices. And clearly by the killing vector field conditions, you know that these are antisymmetric. So now if these span the antisymmetric spaces, you could generate perhaps not perhaps sorry, you can generate all the rotations around x, right? Because this is the basis, and rotations are basically generated by the basis of antisymmetric matrices, right? The generators are the antisymmetric matrices, the rotations. Now, if you're talking about isotropy of space-time, these are basically the Lorentz transformations. The rotations of space-time are Lorentz transformations, and you could also refer to rotations in space-time as rotations of space itself, which you are not talking about right now, which I do want to explore in later times. That's what I mean here by exploring isotropy in space, and then explore isotropy in space-time, where there is a global isotropy, which means Lorentz transformations, and then there is other thing which is restrict the isotropy to space by restricting the curvature. How did the curvature enter here is that you have to, when you consider isotropy in space-time, your killing vector fields that you have, you see there are the isotropy says that there are set of killing vector fields whose derivatives form the basis, right? It doesn't say that there are you get all the killing vector fields around x, which generate all the rotations of around x. No, you only have a span, a set of x, which in turn they generate others. So that's the definition, right? You have a set of KVFs, rotational KVFs, whose derivatives span the antisymmetric space, and then they together generate the whole rotations around x. So the tricky part that I went through the calculations of were that okay, agar derivatives span the entire space and then rotations are generated, but are these rotations that are generated the isometries? Then when you look at the calculations of how this transformation is xi mu of x, for it to be a rotation, your xi mu of x, it can be trivially checked, it has to be something like this, where your j is an antisymmetric matrix, right? And we have that this satisfies the let's say the many set of KVFs are given labeled by A. Now we know that what do we know? We know that plus this is 0, right? Now this if you substitute these j's and x's, you get some condition here. But what's the non-trivial asking here is that if you now set a new x's labeled by some k is equals to summation over your derivatives of the previous whatever you had, right? Okay, now you are okay, yeah. um, let's just say this is this, and this is just the generator, and then you have an x new, right? Yep, more precisely. Okay, yeah, that's how it is. Yep. Okay, I mean, more precisely, if you want to write it, I mean, I would write it like, I mean, I don't know. You could probably write it as some coefficients also. Is a C A new A B. Sorry, this is the new set of labeled by K. I mean, this is K, yeah. This different sort of things, KVS you can generate. And now, does this satisfy the killing vector equation? Is there a non-trivial question? Turns out it does satisfy. I did scratch around here and there a bit, and then concluded that this is the condition that you end up with, and this is indeed 0. So indeed, you do get isotropy. Does imply the rotations, Lorentz transformations, perhaps global isotropy in space-time, which is fun to imagine, I guess. I would definitely want to make a game out of all this isotropies and maximal symmetries, and simulate or create an experience where you could feel these isotropies in space and also space-time isotropy, which is interesting. I would probably spend some time thinking about that at some point of time, but yeah. So that channel is now cleared. So that's where I was struggling for a while there to conclude that. And of course, there are some interesting calculations of if you want to restrict to space, how would you do the calculation? Because then you have to restrict to the rotation. Rotation means that Euclidean metric ka preserve karna. Yeah. So you have to while doing these calculations, I sort of recalled how rotation is defined, how Lorentz transformations are defined. Rotations are defined in a way where you preserve the Euclidean metric. Lorentz transformations are a Lorentzian metric or any signature metric. You get an SOPQ type of thing, and for rotations you get SON sort of thing. By sort of thing I mean the symmetric groups. So yeah, it's interesting. It will be interesting to restrict the curvature to space and do the calculation on that. How do you do that? This will be occupying some when I have free time to do. I'll do them, and that's the fundamental of rotations in space, and that's how it began. Sort of kind of can understand now. कि rotations in Euclidean metric को preserve करता है, and rotations in space time कुछ नहीं होता है. They are just Lorentz transformations in space time, preserving the Lorentzian metric or PQ metric, whatever, PQ signature metric. And then that was second part of maximally symmetric spaces that I talked about. Sorry, that is the first part. Second part is what? Sorry, there is CR is still in the second part. Sorry. So there we understood how isotropy makes sense. Okay. So if you have both isotropy at one point and homogeneity of space, then it's isotropic over all the points, and then you say that it's maximally symmetric space. If you have isotropy around all points and homogeneity in all points, at all points, you have a maximally symmetric space. Now, okay, right. So there's a little proof of how the killing vector fields can be d into d plus 1 by 2 at max. They can be translations or rotations together, the maximum is that. And the the train of thought of proof was slightly confusing about the linear independence arguments. I couldn't understand, but once you kind of understand that, there are still some problems in the calculation of it. So for the calculations of how would you evaluate the Riemann curvature tensor for a maximal symmetric space. In fact, that's how it all began. I wanted to derive the Riemann curvature tensor for a maximally symmetric space. It takes a simple form of it takes a really simple form of this g t mu, g rho mu, and g tau mu, g rho mu. It's a constant. It takes this form, and I wanted to derive this. So during that derivation, there are many things involved again, but it's mostly word. Let's see, how did we do it? I have a photo somewhere. Yep. So you start with the. Okay, let me just import it. Can't do all these calculations. So. Yep. Okay. So pointer. Yep. So you start with this equation. Yeah. It's you can write this equation. Yeah. Any vector satisfies this equation. Okay. It boils from the cyclic property of it comes from the cyclic property of R, which you cyclically permute these and add. For example, not this rho mu nu rho se shuru hoga mu nu rho plus tau nu rho and mu equals to 0. Okay, this is just this. Okay, because you have this basic definition of curvature tensor. Okay, yeah, this is the basic definition of curvature tensor. We should also prove at some point. Learn more about that, the more fundamentals of GR, which I don't have a strong. That's not my strong thing yet. So you start from here, and then you use scaling vector conditions and all that, and this condition, defining condition of Riemann curvature tensor, and you end up with this. But unfortunately, this condition is not. Whatever I got is not matching with apparently with Z's book of Gravity in a Nutshell, and neither with Weinberg's book on gravitation and cosmology. So I don't understand where I'm doing wrong, where I'm doing a mistake. So definitely have to check it with someone. So yeah, apparently this one condition is preventing for me to prove the Riemann curvature tensor. Assume you have this right condition, you can take a derivative of that, and then use this again, another tensorial property, which involves taking double derivatives of a tensor, and and then you have a Riemann curvature tensor relation, and then you substitute the first derivative of scaling vector field, scaling vector field, and you get this. You simplify it, you take a derivative of this previous condition that you get, which is this. Assuming this, you get the right condition, substitute in this, and then you get a good bunch of Greek letters with first derivative on left side and the with plain vector field on left and its first derivative on the right. If you consider translation, the derivative vanishes, then you get a relation on this coefficients due to the linear independence of the solutions to the KVF equation of Zeiss, and then your coefficient vanishes. And then if you consider rotations, your other coefficient sort of vanishes after taking a symmetric combination of that, right? After taking a symmetric combination of that, or an antisymmetric combination of it, perhaps, because the linear independent, you have to reduce it to linearly independent components to say that coefficients are zero. So yeah, you get a symmetry. You end up with a symmetry condition on this under sigma and kappa interchange. You impose that conditions and you get the main equation, okay, which then if you say that if you assume, right, if you assume ki these are independent and they span the antisymmetric matrices and all that, you get symmetry condition on that, which is fine. And then you can just continue and contract the k, rho and kappa indices, and you end up with a nice relation of r. You end up with a nice equation on r sigma mu w. Unfortunately, I didn't get that beautiful relation. In fact, I got a very rather a really bad condition that the Riemann curvature just vanishes, all because I did a mistake here, and I don't know what's the mistake there. But if you resolve this, the calculation is simple. You just simplify this. You deal with the special case of d equals to 2 using this condition also, and also other conditions perhaps. But d equals to 2, you can deal with d equals to 2 with special properties like this, and also turns out that this is satisfied, although this k is some r or something. R may not be constant, but for d equals to 2, this is generally true. This form is generally true, and substitute the other properties, you get the d equals to 2 condition also, and d equals not to d is not 2 condition is pretty straightforward from these calculations, that the scalar curvature is constant, and this is given by r into d minus 1. This is constant, and yeah, that's how it is derived. So that's the chain. I know it's not perfect. I know it's not. I didn't understand every aspects of it, but I did some calculations. I know where I'm lagging, and I know the story of how things are derived. That's probably the important learning. I don't know, but I will keep trying to resolve this conflicts. And really, I'm even confused about how covariant derivatives satisfy Leibniz rule of between, if you just contract two tensors, one of the indices of two tensors, and you apply a covariant derivative, you can use Leibniz rule. I mean, that's interesting, and I want to derive it sometime. I don't know. For now I'm linking it to get the fundamental parts of formulation of GR right, wala thing, because I really have to do that. I need to read Tong and learn the principles behind it. The course that I did I felt like it was a very ad hoc thing, but although it gave me a flavor of GR, I guess, but still, I guess it's first course, so it's good. Yeah, I mean, I appreciate whatever I learned, but I need more, of course, and I'll do that. This is one of the ways where I could do that. So, yep. So that's the whole part of the part 2 of Maximal symmetric spaces, and part 3 is paused for now, where I connect between isometries and conserved quantities, which I really want to do it because the whole point of isometry is sort of boils down to finding conserved quantities, which is good. Which is basically the symmetries of Einstein's equations, right? And the whole symmetries. So you expect Noether's theorem to come around and talk about conserved quantities. It should be a very nice end to the maximally symmetric story. And of course, there are other things that came up between, like the defining equation for Riemann complex tensor, which I linked to again the fundamentals, and the Lie derivative and the KVF connections, which I again linked to the purple link to fundamentals of GR. And of course, this is called generalization to tensor, which we used it in this part, right? which we used it in this part. And then there was an appendix talking about coset manifolds, which would be applied to anti-de Sitter spaces and also hyperbolic spaces. I guess the anti-de Sitter spaces are actually hyperbolic spaces with a negative curvature, basically negative because they have a negative curvature. So yep, there's that, and there it goes. That's how maximally symmetric spaces have gone by in the last 3 or 4 days. I've been trying to think about this part, and then these parts, these calculations I've been doing, so they do take time. And yeah, it's nice. I like it, right? So the thumbnail of this video should be this. Yeah, right? Maybe a more symmetric photo. Yep. Okay. Whew. So yeah, and next I'm working on ADS, DS and all that. Sorry, actually conformal algebras, where there are many channels again, which I'll be doing it after ending this video. We'll go to computer lab, do some additions to this conformal algebra part, and then get on to learning, delving into the details of this conformal algebras. It's going to be a good day. Exciting work ahead. Or again, small bits matter. So these small bits, I'll come back to them and explain this here. Hopefully that will keep my energy up. So bye bye.